Every star you have ever seen is lying to you. That pinprick of light, calm, steady, eternal. It looks peaceful, but inside, a war is raging, so violent, it makes a nuclear bomb look like a candle. And here's the strange part. The only reason that star hasn't torn itself apart is because it is also trying to crush itself to death. Two forces, locked in a battle that lasts millions, sometimes billions of years. And the moment one of them wins, something extraordinary happens. Something that built every atom in your body. This is the hidden life of stars. We tend to think of stars the way ancient people did, as fixed points of light, as decoration. We give them names, draw lines between them, and move on. But stars are not ornaments. They are engines. They are forges. They are engines viges. They are, in a very real sense, the factories where the universe builds complexity. And the story of how a star lives, how it struggles, how it ages and ultimately dies, is one of the most dramatic narratives in all of nature. It just happens to unfold on a timescale so vast that no human will ever watch it from beginning to end. So let's slow the universe down. Let's follow a single star from its first breath to its last. And along the way, let's ask a question most people never think to ask. What does a star actually do all day? It begins, as most great things do, with a cloud. Not a cloud of water, but a cloud of gas, mostly hydrogen, drifting in the empty space between existing stars. These molecular clouds are enormous, sometimes spanning hundreds of light years across, and they are cold. Staggeringly cold. Temperatures hover around 10 to 20 degrees above absolute zero. In these frigid, dark nurseries, nothing seems to be happening. For millions of years, the gas just floats there, thinning out, spreading gently, seemingly content to do nothing at all. But gravity is patient. Somewhere in that cloud, a region becomes just slightly denser than its surroundings. Maybe a nearby supernova sent a shockwave rippling through the gas. Maybe two clouds drifted together and merged. The cause almost doesn't matter. What matters is the consequence. That small, dense patch begins to pull on the gas around it, and as more gas falls inward, the gravitational pull strengthens. More gas arrives. The pull grows stronger, a feedback loop begins, and once it starts, it doesn't stop. The cloud begins to collapse, slowly at first, then faster. As the gas falls inward, it compresses, and compression generates heat. The center of the collapsing cloud grows warmer, then hot, then searingly, blindingly hot. Over the course of roughly 100,000 years, a dense, glowing core forms at the center. Astronomers call this a protostar. It isn't a real star yet. It's more like a promise, a gravitational embryo wrapped in a cocoon of gas and dust. And this is where something remarkable happens. As the core temperature climbs past 10 million degrees, the hydrogen atoms at the center are moving so fast, slamming into each other with such ferocity, that they overcome their natural repulsion. Hydrogen nuclei, protons, fuse together. 4 hydrogen nuclei become 1 helium nucleus, and in the process, a tiny amount of mass disappears. Not much. Roughly 0.7% of the original mass. But that missing mass is converted into energy according to the most famous equation in physics, E equals mc squared. And because the speed of light squared is an extraordinarily large number, even a tiny amount of missing mass releases a staggering amount of energy. The star ignites. This is the moment of birth, the moment when nuclear fusion switches on and a new light appears in the galaxy. And the energy released by fusion does something critical. It pushes outward. It creates an enormous pressure, radiation pressure, that fights against gravity's inward pull. And right here, in this tension between two colossal forces, the star finds its balance. Gravity pulling in. Fusion pushing out. Neither winning, neither losing. A state of equilibrium so stable it can last for billions of years. This is what a star is. Not a ball of fire. Not a burning object. A star is a controlled thermonuclear explosion held in check by its own gravity. It is violence and balance in perfect, precarious harmony. Our own Sun has been in this state for about 4.5 billion years. Every second it converts roughly 600 million tons of hydrogen into helium. Every second, about 4 million tons of matter vanish, transformed into pure energy. That energy, born in the core, begins a journey outward that is almost absurdly slow. You might imagine that light travels from the center of the Sun to its surface at the speed of light. It does not. The core is so dense, so packed with particles, that a photon of energy generated at the center gets absorbed and re-emitted so many times, bouncing in random directions, that it takes somewhere between 100,000 and 1,000,000 years to reach the surface. A photon born in the Sun's core when early humans were first learning to use tools might only now be reaching the surface, leaping into space, and arriving at Earth 8 minutes later. Think about that. The sunlight warming your face is ancient. It was born in the deep interior of a star before your species existed in its current form. You're being touched by something older than civilization. But a star in this main phase of its life, what astronomers call the main sequence, is doing more than just shining. It is slowly, imperceptibly changing. Because fusion doesn't just produce energy, it produces waste. Helium. The helium accumulates in the core like ash in a furnace. And helium, at the temperatures found in a main sequence star's core, does not fuse. It just sits there, inert, building up. Over billions of years, this helium ash displaces the hydrogen fuel. The core gradually becomes a ball of helium surrounded by a shell of hydrogen still undergoing fusion. And here is where the hidden life of a star enters its most dramatic chapter. Because when the hydrogen in the core runs out, the balance breaks. Without fusion pushing outward from the center, gravity takes over. The helium core begins to contract. As it contracts, it heats up. The layers of hydrogen surrounding the core, now compressed and heated by the shrinking core beneath them, begin to fuse with renewed intensity. The star's outer layers, bombarded by this increased energy, begin to expand. Dramatically. The star swells to tens, sometimes hundreds of times its original size. Its surface cools as it stretches, shifting from white or yellow to a deep, glowing red. The star has become a red giant. When our Sun reaches this stage, roughly 5 billion years from now, it will expand past the orbit of Mercury. It will swallow Venus. Whether it will reach Earth is still debated, but it hardly matters. Long before the swollen Sun touches our planet, its increased luminosity will have boiled away the oceans and stripped the atmosphere. Earth will be a scorched, lifeless rock orbiting inside the outer layers of a dying star. But the story doesn't end there. Inside the red giant, the helium core continues to contract and heat. And when the temperature reaches 100 million degrees, something new happens. Helium begins to fuse. 3 helium nuclei smash together to form carbon. Sometimes a 4th helium nucleus joins in, producing oxygen. The star has found a new fuel source. It has bought itself more time. For a star the size of our Sun, this is essentially the final act. Helium fusion produces carbon and oxygen, but the star lacks the mass to compress the core further. It cannot reach the temperatures needed to fuse carbon. So it begins to shed its outer layers, gently pulsing, pushing great shells of gas into space. These expanding clouds of gas, illuminated by the hot core they left behind, create some of the most beautiful objects in the universe. Planetary nebulae, those delicate, glowing shells of color that Hubble made famous. They have nothing to do with planets. The name is a historical accident. They are the exhalations of dying stars. And at the center of each one, the exposed core remains. A dense, Earth-sized ball of carbon and oxygen, glowing white-hot but no longer producing any new energy. A white dwarf. It will cool, slowly, over trillions of years, fading from white to yellow to red to, eventually, a cold, dark cinder. a black dwarf. Though the universe is not old enough for any black dwarfs to exist yet, every white dwarf ever created is still blowing, still cooling, still waiting for an ending that the cosmos hasn't had time to deliver. That is the fate of a small to medium-sized star. Quiet, gentle, in a cosmic sense. A slow fade into darkness. But what about the massive stars? The ones 5, 10, 20 times the mass of our Sun. Their lives are fundamentally different, and their deaths are among the most violent events in the known universe. Massive stars burn through their hydrogen fuel at a furious rate. While our Sun will spend roughly 10 billion years on the main sequence, a star 20 times more massive might exhaust its hydrogen in just 10 million years. 1,000th of the time. They live fast, and they die hard. When a massive star's hydrogen runs out, it does the same thing our Sun will do. It contracts, heats up, and begins fusing helium into carbon. But unlike our Sun, it doesn't stop there. It has enough mass, enough gravitational pressure to keep going. When helium is exhausted, the core contracts again, heats further, and begins fusing carbon into neon and magnesium. When carbon runs out, neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Each new fuel ignites at a higher temperature, burns faster, and produces heavier elements. The star develops layers, like an onion, the hydrogen-burning shell on the outside. Below it, helium burning. Below that, carbon. Then neon, oxygen, silicon. Each layer is thinner, hotter, more desperate than the last, and in the very center, the final product of silicon fusion accumulates: iron. And iron is where the story reaches its crisis. Every fusion reaction before iron releases energy. That energy was what held the star up, what fought against gravity. But iron is different. Fusing iron doesn't release energy. It consumes it. Iron fusion is endothermic. It takes more energy to fuse iron than the reaction produces. So when the core fills with iron, fusion stops. Not gradually, not gently. It stops as if someone flipped a switch, and in that instant, gravity wins. The iron core, roughly the mass of our Sun, but compressed into a volume the size of Earth, collapses. Not slowly, not over thousands of years. In less than a second, the core implodes at a quarter of the speed of light. Protons and electrons are crushed together, forming neutrons. The entire core, a mass greater than the Sun, compresses into a ball roughly 20 kilometers across. A neutron star. The density is almost incomprehensible. A teaspoon of neutron star material would weigh about 6 billion tons, more than every car, truck, ship, and building on Earth combined. The outer layers of the star, still falling inward, slam into this suddenly rigid core and bounce. A shockwave tears outward through the star, ripping it apart. In a single moment, the star releases more energy than our Sun will produce in its entire 10 billion-year lifetime. For a few weeks, this single dying star can outshine an entire galaxy of 100 billion stars. This is a supernova, and in the catastrophic fury of that explosion, something miraculous happens. The temperatures and pressures are so extreme that elements heavier than iron are forged: gold, platinum, uranium. Elements that cannot be created by normal stellar fusion. They are born only in the death throes of massive stars and in the collisions of neutron stars. Every gold ring, every uranium atom in a nuclear reactor, every trace of platinum in a catalytic converter was manufactured in an event of incomprehensible violence billions of years ago. The debris from the supernova, enriched with these heavy elements, expands outward into interstellar space. It mingles with existing clouds of hydrogen and helium. It adds complexity to the raw material of the universe, and eventually, gravity pulls some of that enriched gas together again. A new cloud collapses. A new protostar forms. New planets coalesce from the leftover debris, now containing not just hydrogen and helium, but carbon, oxygen, iron, silicon, gold, all the elements forged in the previous generation of stars. Our solar system formed from such a cloud. The Earth is built from stellar debris. The iron in your blood was forged in a star that died before our sun was born. The calcium in your bones, the oxygen in your lungs, the carbon in your DNA, all of it cycled through at least one, probably several, stellar lifetimes before becoming part of you. This isn't poetry. It isn't metaphor. It is literally, chemically, physically true. You are made of dead stars. But the story has one more layer, one more secret that the hidden life of stars keeps from casual observers. Not all massive stars end as neutron stars. The most massive, those with cores exceeding roughly 3 solar masses after the supernova, collapse past even the neutron star stage. The gravity is simply too strong. No known force in physics can halt the collapse. The matter compresses to a single point of infinite density, a singularity. Space and time around it warp so severely that nothing, not matter, not light, not information, can escape. A black hole forms. And black holes, once thought to be rare cosmic oddities, turn out to be everywhere. Every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center. Ours, called Sagittarius. A star has a mass of roughly 4 million suns. We can't see it directly, but we can watch stars orbiting it, whipping around an invisible point at thousands of kilometers per second. Their orbits tell us something massive is there, something dark, something that bends the fabric of space itself. Some of these supermassive black holes are actively feeding, consuming gas that spirals inward in a superheated disk, emitting jets of energy that can stretch for thousands of light years. These are quasars and active galactic nuclei, among the most luminous objects in the universe, powered ultimately by gravity. The same force that pulled a cloud of cold gas together and birthed a star is, in these extreme cases, creating beacons visible across billions of light-years of space. Stars, in their hidden lives, do more than shine. They build the periodic table. They seed space with the ingredients for planets, for oceans, for organic chemistry, for life. They create the black holes that shape galaxies. They produce the neutrinos that stream through your body by the trillions every second without you feeling a thing. They generate gravitational waves when they collide, ripples in spacetime that we only learned to detect in 2015, opening an entirely new way of observing the cosmos. And yet, for all we've learned, enormous questions remain. We still don't fully understand how supernova explosions actually work. Our computer simulations, even running on the most powerful supercomputers on Earth, struggle to reproduce them. The shockwave that tears the star apart tends to stall in simulations. Something re-energizes it, possibly neutrinos, possibly turbulence, possibly mechanisms we haven't yet identified. The fact that we can watch supernovae happen in real time through our telescopes, yet cannot fully explain the physics driving them, is a humbling reminder of how much remains beyond our grasp. We don't know exactly what happens at the center of a black hole. General relativity predicts a singularity, but general relativity also breaks down at that point. Quantum mechanics should take over, but we don't yet have a theory of quantum gravity that can tell us what replaces the singularity. The interior of a black hole is, right now, a blank page in physics, a place where our best theories confess their incompleteness. We don't fully understand dark matter, which outweighs all the visible stars in the universe by a factor of roughly 5-1. Stars move within halos of dark matter, their orbit shaped by a substance we have never directly detected. We know it's there because of its gravitational effects. But what it is, what particle or field or phenomenon constitutes dark matter, remains one of the deepest open questions in science, and we are only beginning to understand how the first stars formed. The very first generation, born from the pristine hydrogen and helium left over from the Big Bang, with no heavy elements at all. These population-thirst stars, as they're called, have never been directly observed. They may have been enormous, hundreds of times the mass of our Sun, burning hot and fast and dying young, seeding the universe with its first heavy elements. The James Webb Space Telescope is peering into the most distant reaches of the cosmos, looking back in time, searching for the light of these primordial giants. We may find them soon, or we may discover that the early universe was stranger than we imagined. Every new telescope, every new detector, every new observation peels back another layer of the hidden life of stars, and each layer reveals not just answers but deeper questions. That is the nature of science. It doesn't march toward a final truth and stop. It spirals outward, each discovery expanding the frontier of what we don't yet know. When you look up at the night sky tonight, you won't see any of this. You'll see points of light, steady and silent. You won't see the thermonuclear fury, the slow accumulation of helium ash, the desperate onion-layered burning of a massive star approaching its end. You won't see the shock wave, the neutron star, the black hole forming behind a curtain of light. You won't see the gold atoms being forged in the final fraction of a second of a supernova explosion. But you'll know, and that changes the sky. Not the photons reaching your eyes, but the meaning behind them. Every star is a story. Every star is a factory, a furnace, a ticking clock counting down to something dramatic. Some are young and reckless, burning blue-white and squandering their fuel. Some are old and swollen, glowing red, clinging to the last of their reserves. Some have already died, and their light is still traveling toward you, a message from a star that no longer exists. The universe is not quiet. It is not still. It is a churning, cycling, self-renewing engine of creation and destruction, and stars are its beating heart. They take the simplest element in existence, hydrogen, a single proton and a single electron, and through nothing but gravity and time, they transform it into everything, into carbon, and oxygen, and iron, and gold, into planets, into oceans, into the molecules that somehow, under the right conditions, begin to replicate, to evolve, to wonder about the stars that made them. We are the universe looking back at itself, and the stars, in their hidden lives, are the reason we exist to do so. There is something deeply humbling about that, not just the scale of it, the billions of light years, the billions of years, the billions of years, the billions of stars, but the connectedness, the fact that the atoms in your left hand may have come from a different star than the atoms in your right, that you are, quite literally, an assembly of stellar remains, organized by 4 billion years of evolution into something capable of reading these words and feeling a sense of wonder. The hidden life of stars is, in the end, not so hidden. It is written in the periodic table, in the geology of Earth, in the iron core of our planet, in the composition of your blood. The evidence is everywhere, in everything, woven into the fabric of the physical world. We just had to learn how to read it, and we are still learning.